working on the surroundings by the expanding balloon. Okay, so let's talk about exchanging energy between system and surroundings. Okay, there's exchange of heat energy. So we talked about how heat energy, or the exchange of heat energy, is Q, which equals the mass times the specific heat times the change in temperature. And we talked about exchange of work, where work equals the negative pressure times the change in volume. Recall that the change in internal energy that occurs during a chemical reaction, so that change in E, internal energy, is a measure of all of the energy, heat and work, exchanged with the surroundings, which is that exchange in energy equals Q plus W. Therefore, we can measure the changes in temperature to calculate heat and the changes in volume to calculate work that occur during a chemical reaction, then sum them together to calculate the change in energy. However, an easier way to obtain the value of change in energy for a chemical reaction is to force all the energy changes associated with the reaction to manifest itself as heat rather than work. We can then measure the temperature change caused by the heat flow. So, measuring change in energy, sorry y'all, it's going to be a while from, calorimetry at constant volume. Because the change in energy equals Q plus W, we can determine the change in energy by measuring Q and W. Q, remember, is heat, and W is work. In practice, it's easiest to do a process in such a way that there is no change in volume, so W equals 0. So if we can keep the volume constant, that will make the work equal 0, and that means that the energy of the system is the heat of the system. In practice, we can observe the temperature changes of individual chemicals involved in a reaction. So instead, we measure the temperature change in the surroundings. So we can't really measure the individual chemicals and their temperature changes, but we can measure the temperature changes in the surroundings. So we use insulated control surroundings. Therefore, the Q of the system is the negative Q of the surroundings. Remember, if the heat exchange is going to be complete and even. The surrounding area is called the bomb calorimeter and is usually made of a sealed insulated container filled with water. So that means the heat of the surroundings equals the heat of the calorimeter, which equals the negative heat of the system. Okay, so remember, Q and negative Q, they're going to be the same number. It's just that the negative is going to show the surroundings, or the system, and then the positive is going to show the surroundings. Okay, so calorimetry is used to measure thermal energy exchange between reaction and surroundings. A bomb calorimeter has a constant volume and is used to measure the change in energy for combustion reactions. A calorimeter can keep the volume constant, so we can measure just the change in temperature. Therefore, we can measure the Q. Therefore, we can measure the change in energy. The heat capacity of the calorimeter is the amount of heat absorbed by the calorimeter for each degree rise in temperature, and it's called the calorimeter constant. So each type of calorimeter will have a certain heat capacity. Now, these are fancy calorimeters. This is a fancy calorimeter with a thermometer and an ignition wire and everything. You can also use this thing called a coffee cup calorimeter, and it's basically like 2 styrofoam coffee cups with a top and a place where you can stick in a thermometer, and it works just as well. So let's look at an example. It says measuring the change in energy reaction in a bomb calorimeter. When 1.010 grams of sucrose undergoes combustion in a bomb calorimeter, the temperature rises from 24.92 degrees Celsius to 28.33 degrees Celsius. Find the change in energy of the reaction for the combustion of sucrose in kilojoules per mole sucrose. The heat capacity of the bomb calorimeter determined by a separate experiment is 4.90 kilojoules per degree Celsius. You can ignore the heat capacity of the small sample of sucrose because it's negligible compared to the heat capacity of the calorimeter. So you're given the mass of the sucrose, We're given the initial temperature, the final temperature, and the heat capacity. Sorry, the heat capacity. And we're asked to find the change in energy of the reaction. Well, it's in a calorimeter. It's in a bomb calorimeter. That means the volume is constant. So we don't have to worry about the work. We just want to worry about the Q. Okay, so the conceptual plan has 3 parts. The first part, we're going to use the temperature change and the heat capacity of the calorimeter to find the Q of the calorimeter. Second part, we use the Q of calorimeter to get the Q of the reaction. That just involves changing the sign. Since the bomb calorimeter ensures a constant volume, Q of the reaction is equal to the change in energy of the reaction for the amount of sucrose burned. In the third part, we're going to divide by the Q of the reaction by the number of moles of sucrose to determine the change in energy per mole of sucrose. Okay, so first we're going to use this. Remember that this is the Q formula. This is the formula for Q. And we are just plugging in our specific heat, or our heat capacity, and the change in temperature. And then we're just changing the sign. That's what this is doing right here. And then we're going to take the Q of the reaction divided by the moles of the sucrose to find the total change in energy of the reaction. Okay, so remember, molar mass is 342.3 grams per mole for sucrose. Okay, so let's look at this work. So first we found the change in temperature. That's going to be 3.41 degrees Celsius. That's the final temperature minus the initial. Then we're going to plug it in. So we plug in our given specific heat, or heat capacity, sorry. And then the change in temperature, and that gives us 16.7 kilojoules. Okay, so that is the Q of the calorimeter. Remember, think of it this way: the calorimeter is the surroundings. Okay, the calorimeter is considered the surroundings. We don't want the Q of the surroundings. We want the Q of the reaction, which is the system, right? So that's why we have to change the sign, because we found the Q of the surroundings, and we know that it's the same value. It's just a different sign. And so we changed the sign, negative 16.7 kilojoules per mole, or kilojoules. Well, now we know that there are negative 16.7 kilojoules, and we know that there's 1.10 grams. That's what we're given. This is our given mass, right? And we find the number of moles by dividing by the molar mass. They basically did 2 different steps. So they found the amount of moles here. You found the number of moles using the molar mass, okay? And then they took the amount of kilojoules and divided by the number of moles that they got, and they got negative 5.66 times 10 to the third kilojoules per mole. So it says the units in the answer are in kilojoules are correct. For the change in internal energy, the sign is that change in energy of the reaction is negative, as it should be for a combustion reaction that gives off energy. This is a combustion reaction. It's going to give off energy. That means that the system, which is the reaction, is doing work. So it should be negative. Okay. And so we're going to stop here for today. We'll talk about enthalpy